some text here. So what's going on is we need to talk about a word that is going to show up on the AP test, differentiable. Differentiable. Okay? So instead of just telling you what differentiable means, I'm going to draw a picture of a graph that is continuous and differentiable at x equals 5. And then I'm going to draw a graph that is continuous but not differentiable at x equals 5. And I'm going to see if you can figure out what it means for something to be differentiable. Okay? Now it says right here what it means, but you might not understand exactly what the meaning of this sentence is. So just trying to see if you guys can figure out from an example and a non-example what differentiable means. Okay, so I have a graph that goes like this. Okay? And at 5, this thing is continuous and differentiable. Okay? Here's another graph. Where at 5 it is continuous, but it is not differentiable. Okay? So here's the basic gist of it. It has to do with the tangent line. Okay? So if you were to pick a point here and a point at 5 and draw a secant line, it would look like this. And if you brought that point inward towards 5, that bottom point, as you move it inward, closer and closer, you eventually get to where it looks sort of like you're getting a tangent line like this. So I'll draw my first tangent line in blue. Okay? But if you were doing this from the right side, you would not be getting that result. Right? Let's do this in red. So you would be picking 5 and a point after 5. There's your secant line. As you move the right point towards the left point, the tangent line is looking more and more horizontal. See? I mean the secant line. So it would appear that the left side of this graph and the right side of this graph have different tangent lines, if that makes sense. The tangent lines don't behave the same way. So although the y values agree, the slopes do not. Okay, so if I had to give everyday adjectives to this, I would say that this graph is connected and smooth. But I would say that this one is connected and how about just not smooth? Differentiability has to do with smoothness. That's what it really has to do with. So imagine if you're on a roller coaster. Has anyone ridden on Ghost Rider at Knott's Berry Farm? Does anyone else get a headache on that ride? Because I get a headache every time I ride that thing. It's because of the non-differentiable points on that track. Okay? So next time, just go up to the operator and say, man, you guys got to do something about those non-differentiable points. But in math, these graphs, they have all sorts of weird, sharp points on them because what they are is just parabolas glued to other parabolas and a line glued to a parabola, so they're going to look jagged. And when they look jagged, we have no differentiability. Okay? All right, so what does it mean more formally? You can't just say on the AP test, oh, yeah, the graph is not smooth. You can't do that. Okay, it's not the official way to do it. So what does it mean for f prime not to exist at a point? Because it says right here, a function is called differentiable at a point C if f prime of C exists. So you can see that it is not differentiable at 5 on that second graph. No derivative at that point. So the derivative is what, d and e, or undefined, or how do you actually say it? So I want to remind you that the derivative is actually a limit. This is really important you understand this. The derivative is a limit, right? Recall, f prime of c is actually a limit. Namely, it is this limit. It's limo f of c plus h minus f of c all over h. So why am I making such a big deal of this? It's because when we say a derivative doesn't exist, what we're saying is that there is a limit that's d and e, see? A derivative is a limit. And in order for a limit to exist, one case of which would be a derivative to exist, we have to agree on the left and right limits. So we call these left-hand derivative and right-hand derivative. Okay? They are called the one-sided derivatives, and they are simply limo left f of c plus h minus f of c all over h. That's your left-hand derivative. I'll call it LHD. And then we have right-hand derivative, which is the same thing only with a plus. Limo plus. They're exactly the same, except one is left limit, one is right limit. Okay, so someone says, hey, I want you to show me that the derivative is different on each side. What they're really asking you to do is find the limit left and limit right and show that they're not equal. That's what we're doing in a second. Okay, so let's say you are asked to prove that a function is differentiable at a point. What you need to do is, first of all, you would have to prove that it's continuous. This is really important too, that you understand. On my graph, right, I drew a picture of a graph that was continuous at 5, remember? But it was not differentiable. That's because it had an abrupt change in slope. If I had drawn a picture like this, okay, and asked you, is it differentiable, you would have said no. But you would have given a different reason. If I said, is this differentiable, you would say, no, Mr. Shore, it's not even continuous. How could it be differentiable? Okay? You don't need to do any limits left and limits right. One of the criteria for a graph to be differentiable is that it's continuous. So this is automatic not differentiable. Why? Because it's not continuous. But if it is continuous and filled in, and somebody asks you to check for differentiability, then you do your limits. Okay, so first thing you have to understand here is that f of x needs to be continuous in order for there to be differentiability. If I tell you I'm thinking about a differentiable graph, you can assume it's continuous. If I say I'm thinking about a continuous graph, you cannot assume it is differentiable. I'll show you what I mean. This is a continuous graph that is not differentiable. There are several jagged points. These are all corners, yeah. If it's like an arch connected to an arch, we call that a cusp. So listen, this thing is continuous, but it's not differentiable. There are many points where it loses differentiability. However, if I say I'm thinking of a graph that is differentiable, that means a ride like at Magic Mountain where everything seems so well engineered and smooth. I've never gotten a headache at Magic Mountain. Maybe on Ninja. Okay? So you got this neat roller coaster, right? This is not a function, but this thing is continuous and differentiable. If I'm saying that it's a nice differentiable graph, this is a roller coaster. If I'm saying it's differentiable, it's implied that I'm talking about it being continuous also. Okay? If somebody says, oh, I'm thinking of a continuous graph, you cannot assume it's differentiable. If they say you're thinking of a differentiable graph, then you can assume it's continuous. Okay. All right. So what you have to do is you have to first prove it's continuous. After you've proven it's continuous, you may then check your limo left and limo right for the difference quotient. Okay, so that's exactly what we're going to do on this example. All right, so what we're going to do on this graph is we're going to prove it's continuous, and we're going to prove that it's not differentiable. Does anyone know where the sharp turn is in this graph? Look closely. 1, 2. Yeah, it's a little hard to see, but there is a sharp turn right here. Now you might say, oh, that's not a big deal. That would be a big deal if you're on a roller coaster. Okay? That would hurt. That would shake your brain. Okay? And you'd probably jolt against that seatbelt, that harness. Okay? So let's go ahead and try this out. Let's do this part first. Okay, to show that f is continuous, we would write limit as x goes to 1 from the left of f of x. Is this indeed equal to limit as x goes to 1 from the right of f of x, and is that in turn equal to f of 1? So this is our little continuity test. This is chapter 2 stuff, right? Okay, then you would just plug in the left piece. So there's your left piece. And so notice I stopped writing the little superscript. It's not necessary. I've already chosen the left piece, so I can just call it x goes to 1. Is this the same as limit as x goes to 1 for the right piece? And then what about f of 1? How do you decide which function you're going to use for f of 1? There's two parts, right? You got to look at the domain, right? So f of 1 has to be evaluated using this first one because it has x less than or equal to 1. Okay, so we will be using 1 plus 1 quantity squared minus 2. You got to write the correct stuff. If you wrote the other one, it would technically be a wrong proof. Okay, well, all of these can be solved by direct substitution, and you get 2 equals 2 equals 2. Nice little three-part proof there. Okay, so we know it's continuous, and look, the graph looks connected, right? But you can't use your eyes to verify it. There might be a tiny little gap we can't see there. We just showed that that gap is closed. So we're good on continuity. Now let's show that it is not differentiable. Okay, so let's go on. I'll do that in green. Okay, so to show, second half of the sentence, to show that f is not differentiable, we write okay, we are trying to show that limo left for the difference quotient at 1, so it's basically 1 plus h minus f of 1 over h. We're trying to show that this is not equal to limo right for the difference quotient at 1. Okay, so we're going to substitute in 1 plus h into our first expression. So this will just, since we're already using the left piece, we'll drop the little superscript minus sign there. So it's going to be basically 1 plus h plus 1 squared minus 2 minus, and then 1 plus 1 squared minus 2. And then let's look at the right side limit as well. So for the right piece, it's negative. It's supposed to be x minus 2, but we're putting in a 1 plus h. 1 plus h minus 2 squared plus 3 minus, and then 1 minus 2 plus 1 minus 2 squared plus 3 all over h. So that's a square right there. And you'll see if you work all this out that one side comes out to 4 and the other limit comes out to 2. Those are different slopes. So we showed that 4 is not equal to 2. In other words, you can work it out if you want. It's kind of a lot of work. You got to FOIL that, and it gives you h squared plus 4h plus 1 minus 2 minus 2 all over h. And then some stuff cancels out. This should say h squared plus 4h plus 4 minus 2 minus 2. Okay, so this cancels out. And you factor out an h. And then this reduces by division. Okay, so you plug in the remaining h's at 0, remember? Okay, so this just comes out to 4 on the left. Let's look at that other limit. I hate doing these limits, but I have to establish it. Okay, so we have, it looks like that's going to be like an h minus 1 and it's squared, so it's basically negative h squared minus 2h plus 1 plus 3 minus 4. And then if you distribute properly, there's a negative to distribute. You have a negative h squared plus 2h minus 1 plus 3 minus 4. Okay, so this is a moment where I made an error, but I know that I did. Does anyone see why I know for sure I made a mistake? What doesn't happen? The non-H stuff's not canceling, so this is always a sign that you did something wrong. Did anyone catch my error? You see it, Hunter?
I think it's up top.
Oh, I think I see it too. Is it right here? There's another negative there, isn't there? Yes, it's a difference in the two functions, and that function had a negative there, didn't it? Ah, okay, so this is a 2. Okay, so I don't mind making a mistake if we learn from it, right? It's important that we know when there's something wrong. I was pretty sure there's something wrong there. Okay, so that's now gone like it should be. And we get, if you factor out an h, you have negative h plus 2 right here. All over h. This is an h. Okay, then you can reduce it. All right, so in the end, this side was 4, and if you plug in a remaining 0, you get 2 on this side. So what exactly does this mean? This means that the tangent lines on one side are approaching the slope of 4, but the tangent lines on the other side are approaching the slope of 2. And if you go back to the graph, and you draw in those tangent lines, you'll see what I mean. Okay, imagine drawing on the left side, drawing tangent lines. You'd probably come up with something like this. So let's do this left side in blue. That thing has a slope of 4, see? That tangent line. But if you go to the right side and try to draw, let's draw that one in green, the tangent line has only slope 2. And you can't have two different tangent lines at the same point. That doesn't even make sense. So this is an example of a point that's not differentiable. All the other points on that graph are perfectly fine. They're all differentiable and connected and smooth and all that good stuff. Okay? So that's how you show it. It's a lot of work for one-sided derivative. This is how you do number 31 in the homework. You're supposed to do it completely like this. So I'm sorry, but no shortcuts on derivatives yet. All right, so that's my example. And then I wanted to show you Mr. Slope Guy real quick, because he's cool. And he'll help you with this activity. So I saw this on, no, Pinterest. Isn't he cool? This is Mr. Slope Guy. So the plus means that this line is positively sloped. See how it's going up? Positive slope. And then the minus here means that this is negatively sloped. What does the U here mean for this line? Undefined slope. That's right. Vertical line is an undefined slope, U. And a horizontal line has slope. Undefined, a horizontal line has slope 0. Yes. Mr. Slope Guy. I'd like to take credit for him, but I can't. I got him off of Pinterest.